I'd first like to thank all the organizers for kindly inviting me to this grand event. It's a great pleasure and honor to be able to speak here. A really massive event. I've never been to such a big conference before. So in this talk, I'll be arguing for certain spectral bounds, which should apply to every consistent six-dimensional n equals 1 supergravity effective field theory. In fact, the bounds will be very rigorously derived in six-dimensional F theory. But along the way, we will see how they may possibly apply also to the general supergravity setting without relying a priori on the string theoretic origin of the effective field theories. So the talk will base mainly on this collaboration with Hotel Birkar, who is an algebraic geometer at Tsinghua University. Of these two papers, one is a physics version and the other is going to be a math version. So both came out last week. And hopefully you will find at least one of them interesting, depending on where in the spectrum you are sitting at between physics and math. So as you will see, many of the tricks that we develop and use in this work are going to be rather algebra geometric. Being a physicist myself, however, I will be speaking in a physical language in this talk. And perhaps due to this mixed nature of the talk, there is a big chance that I lose both mathematicians and physicists in the audience. So before I lose all of you, let me in fact start by announcing our main result in this slide, both in physics and in math versions. So if you are a physicist, then what we do here is to propose this conjecture/theorem, which goes like this. So in every consistent six-dimensional n equals 1 supergravity EFT, and in particular in any six-dimensional F theory, the number of tensor multiplets, which I'll denote by capital T throughout the talk, is uniformly bounded from above by this number 567. But if you are a geometer, then perhaps this statement does not make too much sense to you. Then instead, here is a translation which goes like this. So assume that the pair Z comma B is projective 1/6 log canonical of complex dimension 2, and Z is a rational surface, and 12 times K plus B is linearly equivalent to 0, where K is the canonical divisor of the surface Z. Then our claim is that the rank of the Picard group of the surface Z is bounded from above by 568. So this is our main result. And if at least one of them makes sense to you, then hopefully by the end of the talk, you will have found that the other also does. So here is the outline of this talk. The plan is very simple. I'll start by motivating our program and clarifying the scope of this talk. And next, I will give some rudiments of six-dimensional F theory, reminding you of how particles and strings are encoded in the geometry of F theory compactifications. Then I will address universal bounds, focusing on the tensor spectrum. But I won't give too much of details here, though. I will, in fact, start by spelling out a couple of key structures involved, and I will briefly describe the strategy and the outcome of the strategy when used to the setup. And I will clarify the rationale behind the boundedness before actually getting to the explicit bounds. And after all that, I will finish with a quick summary and discussion. So let's start with the introduction. Oops, no. So what we will analyze in this talk is the string vacua, which are going to be the Calabi-Yau variety in one way or another. So to begin with, some concrete facts about them. So what do we know about their actual explicit geometric construction? So a particularly useful way to construct them is to carve them out in a simpler ambient variety as the zero locus of polynomials, or more generally of global sections. Then a big data set arises of over 1 billion already for trefoils. In fact, this number, 1 billion, despite being large already, is only a very conservative estimate because it only counts the 4-dimensional reflexive polytopes, each of which leads to multiple different Calabi-Yau trefoils generically. And as for the actual Calabi-Yau counting, we expect order of 10 to the 400, which is a really, really huge number. And what's perhaps more interesting is that a majority of these manifolds turn out to be admitting elliptic vibration structures, at least vibrationally. This might have been an artifact of this particular construction being used here, but still it's very interesting and even surprising to realize this fact. So two simple observations from here. A, there exists a vast number of different Calabi-Yau varieties, and B, the same is true of the elliptic ones. Okay, now switching gears to physics, the quantum gravity theory in the UV, i.e. at very high energies, is very much constrained, as reflected already by the sort of uniqueness of string theory. Nevertheless, due to the multitude of the allowed internal manifolds of string theory, the theory leads to a plethora of low-energy effective field theories, or string EFTs for short, which form the vast string landscape. And here's our general motivation. So we consider the entire set of effective field theories, which splits into the landscape of the consistent UV complete quantum gravity theories and its complement, the swampland. And then obviously the former set contains the string landscape as a vast subset, proper or not, within the landscape. Then we aim to distinguish the effective field theories in the landscape from those in the swampland by revealing general constraints of quantum gravity theory, often called quantum gravity conjectures due to their conjectural nature. And to this end, the string landscape serves as an excellent guiding principle if we can ever extract common physical properties of the so many string EFTs. In particular, we can try to establish appropriate universal geometric properties of the internal spaces in order to find any general properties that are exhibited at least by all of these string EFTs coming from geometric compactifications. And the hope here is this way we might be able to gain some fruitful insights on quantum gravity conjectures in general. Now, the EFTs in scrutiny today will be the 6-dimensional supergravity EFTs with minimal supersymmetry, so it's n equal 1 supergravity. Their field content organized into the supermultiplets of these 4 types, 1 gravity multiplet, V vectors, H hypers, and T tensors. That's how I denote their numbers. The supergravity action takes this specific form subject to the supersymmetry. But I'm not going to detail the action except pointing out that the SO1, T vectors A and Di's here are the parameters known as the anomaly coefficients. And we will shortly come back to them. Now, given this concrete arena, one of the most fundamental and basic questions we can ask concerns its finiteness, i.e., one might ask if the number of consistent theories is finite. And relatedly, our major question today is going to be if the discrete parameters such as the spectrum data, VHT, are going to be bounded from above or not. So in order to answer this question, most of the previous attempts, if not all, relied heavily on the anomaly cancellation, which constrained the anomaly coefficients, the aforementioned A and BI vectors, in terms of the spectrum data, VHT, as well as more detailed charge data. And obviously, these anomaly constraints rule out so many EFTs, so they are all, each of them is going to be some codimension 1 condition in the full parameter space. As it turns out, however, some infinite families of EFTs do survive with arbitrarily high spectrum data VHT, as first realized almost 15 years ago firstly by these papers. So at this point, one could have given up on the idea of a finite notion in the set of EFTs, consistent ones. But interestingly, some ideas came out, interesting ones, via the so-called completeness hypothesis. So upon applying this criterion to the two-form tensor fields of six-dimensional supergravity theory, one can expect that strings of various different charges should all be present in the theory. Then the unitarity of the worldsheet theories of those strings turns out to rule out some of those infinite families of EFTs despite their anomaly consistency. Furthermore, the same idea turns out to impose some explicit upper bound even on the U1 rank of your six-dimensional EFT, pretty tight one here, although this probably is going to be, well, generically is going to be only part of the full vector data V. So one might think perhaps some more general spectral bounds might also arise if some basic constraints like anomalies are appropriately combined with a reasonable enough quantum gravity conjecture, such as the completeness here. So here's what this talk will be about. In this talk, we'll be deriving some of the spectral bounds in a systematic fashion, but more from the top-down angle, at least to start with, via imposing geometric constraints of six-dimensional F theory. And this is going to be some set of consistency constraints from the geometry. Then, building upon the lesson from there, we will infer the bottom-up rationale by rephrasing the relevant geometric constraints in the language of effective field theories. And yes, I must say that the way we derive the bounds is to be compared with some of the exciting complementary approaches. In particular, Kibafasu at Harvard and Hamada Logis at KEK take a bottom-up route via the anomaly constraints together with some of the quantum gravity conjectures in the spirit of the speculation we just had a slide ago. And it will be interesting to clarify the connections better. So I'm done with the motivation and scope. So let me start giving you some rudiments of 60F theory, which is going to be the main arena for our analysis in this talk. So 60F theory is a type 2D string theory compactified on a complex twofold Z2, but with some seven branes around on some complex curves there. And therefore, the axial dilaton will vary internally, solved by this internal configuration of the seven branes. And here, the dilaton profile, or equivalently the seven brane configuration, can be encoded in an elliptic fibration over the internal space Z2, of which total space is a Calabi threefold Y3. Such a fibration admits a Weierstrass description of this form, where F and G are sections of 4 and 6 times the anti-canonical bundle of Z. And the discriminant delta is 4fq plus 27g squared, whose vanishing loci support the singular fibers in this elliptic fibration pi, indicating in turn that the 7 brane stacks are located on these loci. In fact, the singular fibers encode not only the 7 brane location, but also the vector and the hypermultiplex. Firstly, the singular fibers on the codimension 1 loci on the base Z, which I will call codimension 1 singular fibers, in fact, they result in vector multiplex. The so-called minimal Kodaira fibers are classified via the vanishing orders of these sections F, G, and delta, and they are immediately translated into the gauge algebras of the resulting vector multiplex. And the algebras are of a Lie type arising at finite distance in the moduli space. But obviously, missing in the table are the vanishing orders that are higher than 4, 6, and 12. And the corresponding fibers are called non-minimal fibers. Then, despite the fact that these fibers cannot be crampantly resolved into a smooth Calabi-Yau variety, the brane collisions of this type were analyzed properly in these works via the base blow-ups. And then the physics was interpreted as the affinization of the gauge algebras, which occur at infinite distance in the moduli space, and in turn as the decompactifications of the space-time where your EFTs are living in. On the other hand, the codimension 2 singular fibers at points of the base Z, the surface Z, are responsible for the hypermultiplex. The singularities further enhance at those points, and localized metamultiplex arise charged under the gauge algebras of the 7 branes hitting the specific point you are localizing your metamultiplex. Now, unlike the vectors and hypers, the tensor multiplets are encoded purely in the topology of the base. They arise simply from the dimensional reduction of the Ramon-Ramon 4-form field over the internal harmonic 2 forms of the internal space Z. And therefore, the tensor count T is going to be identified with the rank of the Picard group of the internal space Z, modulo this trivial shift by the gravity count. And today we'll be addressing a uniform bound on this Picard rank rho, focusing on the tensor sector. Now that we are going to focus on the tensor sector, you might ask, why did we then have to discuss the vectors and hypers? And that's because these 3 sectors of the theory are intimately connected, in particular via the notion of conformal matter. So as discussed, the localized matter arises at a codimension 2 point of Z, where the fiber of singularity enhances. But if the singularity enhances too severely to go beyond this minimality bound of 4, 6, 12, then what we have is the conformal matter instead. Then we just perform base blow-ups at the point, increasing the Picard rank of the internal space, thereby producing additional tensor multiplets. And therefore, such blow-ups, each of them is a tensor transition. Okay, enough of the particles and the fields. Now, just like the 7 branes on a divisor lead to vector multiplets, an effective string arises from the 3 branes on a complex curve C inside the internal space Z. Then, as it turns out, the resulting string type is completely determined by the precise way the curve C is embedded in the surface Z. And the viable base twofolds were classified. The full list consists of the projective plane P2, the Alike surface, the Hertzsprung surfaces, as well as their blow-ups, amongst which all but P2 and the Alike is P1 fibered. And here, the way the P1 fiber is embedded in Z as a fiber is universal. So we'd say that the 6-dimensional FD vacua are genetically equipped with a certain distinguished string associated with this universal P1 fiber, which turns out to be the heterotic string. So in the rest of this talk, we will focus on such generic basis because the two exceptions, P2 and the Like, have fairly small Picard ranks, 1 and 10, which are going to be irrelevant for our purpose of bounding T. Okay, so having recalled some basics of F theory, we are now ready to address universal bounds on the tensor spectrum. So I will first spell out two key structures in geometry, which are going to play a crucial role in bounding the tensor spectrum T. One is the fibration structure that the internal space Z is P1 fibered. So as discussed, the generic base Z for our F3 background admits such a fibration structure, and we may assume this for the purpose of our bounding program here, as discussed. And the other key is the singularity structure that the pair Z comma B is 1/6 low canonical, or 1/6 LC for short. And here, the divisor B is roughly identified with the discriminator locus delta of the elliptic fibration modulo this scaling by 12. To be precise, the divisor B is defined via the discriminant divisor and the moduli divisors, lambda and m. So the former captures the singularity structure of the elliptic fibration, whether the singularities are coming from the base or the fiber or the total space. And the latter, the moduli part, is defined by its class being in minus k minus lambda, along with a certain positivity property. But in this talk, at least, we will just roughly identify this divisor B as a whole with the discriminator locus delta, although there is some subtle difference. But just to give you the idea, let's just consider 12 times B as the discriminator loci delta. And perhaps, maybe more crucially, this notion of 1/6 LCness might be new to many of the physicists in the audience, at least, like it had been the case to me until I started talking with Pocher. So let me briefly describe how it is precisely defined. Well, not precise, but like, at least here is this working definition for us, just to give you an idea. So we say that the pair Z comma B is epsilon log canonical, or epsilon LC in general for some positive epsilon, if every coefficient of the divisor B is less than or equal to 1 minus epsilon. Okay, and here I say 1/6 LC. So with epsilon equals 1/6, the claim we make is that the divisor B is, well, its coefficient, every coefficient of divisor B is less equal 5/6. Or equivalently, what we are saying is that 12 times B, which is roughly delta, has coefficient less equal 10. Yes. Really, you expand your divisor into the components. And you look at the coefficient of each of these components. Yes. Right? Then you can check that this is true by looking at each of these Kodaira types that could possibly arise in the degeneration of this elliptic fibration at some coordination loci in the base. So as we've just listed here for all possibilities for the Kodaira types. Then, interestingly, each of these two geometric structures turns out to have a very natural physical interpretation. So let me discuss each of them in turn. Firstly, Z is P1 fibered if and only if the corresponding effective field theory contains a heterotic string, which at finite distance in the moduli space is going to be tensionful. And we discussed this at least in the Riemann part already. And secondly, the pair Z comma B is 1/6 low canonical if and only if the dimension of the space-time is fixed to D equals 6. And you might think, okay, this is a very trivial criterion to impose, but let me explain what I mean by this. So, as discussed, this 1/6 LCness of the pair demands that the divisor 12 times B which is roughly delta, has coefficients less equal 10. Then just from this, we gain this intuition that essentially the criterion refrains the codimension 1 fibers of the elliptic vibration from becoming non-minimal. And now, given that the non-minimality of the elliptic fiber singularities trigger the space-time decompactification, now we have this physical principle corresponding to this singularity structure, which is that the space-time is kept 6-dimensional. And indeed, this is some obvious thing we can impose because what we are bounding is the effective field theory spectrum of 6-dimensional theories, not in higher dimensions. And very interestingly, these two key principles in physics, or these two geometric principles, are intimately connecting with the two universal asymptotic physics as conjectured by the Merger-String conjecture. So the precise claim of this conjecture was this: very generally, at infinite distance in the moduli space of quantum gravity theory, either A or B happens, either a tensionless critical string emerges or the space-time decompactifies. In other words, a light critical string must emerge unless the space-time decompactifies at infinite distance in the moduli space. So that's the claim. And now what we are considering is not the boundary of the moduli space, but we are just generically imagining some bulk of the moduli space given a theory. So this way, the fact that these two are precisely these two asymptotic behaviors seems to indicate that the general bounds, such as the spectral bound we are trying to aim at, arise via characteristic asymptotic physics, which is an interesting point of view to have. Yes? Yes? That was codimension 2. That was codimension 2. That was meta. So localized codimension 2 fiber being non-minimal doesn't mean too much, too severe, as long as it's controlled enough. But here I'm talking codimension 1. We interpret this as a decompactification. If it happens at codimension 1, not at codimension 2. If it's at codimension 2, as you say, there's nothing wrong. It's a conformal meta. But here I'm talking codimension 1 fibers. Yeah, it's very different. Okay, now for the bounding strategy in a nutshell. Our bidirectional tricks are easily statable in physical language too. So what we are doing is the following. We blow Z down to a Hertzsprung surface Z naught, like this, and then we go through a sequence of blow-ups here on the right, which are the tensor transitions, each generating one additional tensor multiplier to the theory. And B, we keep track of the induced devices, BIs, along the way by zooming in onto the conformal meta. And C, we impose effectiveness and 1/6 elseness on the induced BIs so that the 7 branes must wrap a supersymmetric cycle and the space-time dimension is fixed to 6. Or to put it simply, we could as well say that the conformal meta better not be too thin nor too thick. Then the idea here is, in A, the step A here, the surface Z naught is going to be blown up as many times as the constraints in C allow. Then the Picard rank of the starting point Z is bounded from above by that of the endpoint of this blow-up sequence ZR, which we bound. So this way we bound R, the length of this blow-up sequence, rho, the Picard rank, and the T, the tensor count, all together. Okay, and here's the outcome. As it turns out, the number of blow-ups R cannot be arbitrarily high, which is about the boundedness at the abstract level. But moreover, even more, an explicit upper bound arises on R. And as of now, we have been able to show that this number R, the length of the blow-up sequence, like the length of the tensor transitions, cannot go beyond 566. This is by no means an optimal bound, but this serves as a proof of principle for sure. Then we have a conjecture/theorem for physicists. So it is a conjecture for effective theorists, say, and a theorem for string theorists that the number of tensor multiplets T is bounded uniformly from above by this number 5, 6, 7. And it is a theorem for geometers that the surface Z, complex surface Z, which can serve as a base of an elliptic Calabi-Yau 3 variety, which is necessarily subject to these three criteria. For such a surface, we claim that the Picard rank of Z is bounded from above by 568. So this is a uniform bound that applies to every such surface that can be a base of such an elliptic Calabi-Yau 3 variety. So that's the upshot. And maybe in the remaining 15 minutes or so, 20, 15, how many minutes do I have? 20? Okay. Yeah, in the remaining maybe 20 minutes, I'll be giving you a little bit of details of how this actually works. And maybe I'm not giving you all the details, but at least I wanted to give you the idea of how this arises. Okay. So to start with, it proves to be extremely useful to define the notion of the horizontal multiplicity. And for the preparation first, the idea here is to make full use of the fact that all of these surfaces are P1 fibered over the common base P1b. So they are all P1 fibrations here. And as discussed, we starting from the B here, the defining data, we are inducing B0, BIs, and so on up here through this sequence of blow-ups and also blow-down involved. So these induced divisors BI, as discussed, they are keeping track of the 7-brane loci along this sequence of tensor transitions. Then what we are doing is to split each BI into the horizontal part, which are denoted by BIH, and the vertical part, BIV, with respect to the P1 vibration PI at ith level. So we can do that, given that every ZI is P1 fibered. Then, in this setting, we define the horizontal multiplicity, HI, as the multiplicity of this horizontal divisor, BIH, at the blow-up point, small zi, inside big Zi. So this is where the blow-up is happening. And then you read off the multiplicity of the horizontal divisor only. So that's why it's called the horizontal multiplicity. So again, we are looking only at this BIH part in defining this HI. And physically, what this means is that identifying these B's as the 7-brane loci, what we are considering here is only the horizontal part, which means that we are only looking at the perturbative 7-brane sector, which coupled to the heterotic string. And we just read off the HI in this manner. Then this HI turns out to play the role of a very nice order parameter, which controls the blow-up sequence. Now, a very interesting observation to be made here is that 12 times HI for any I has to be integer. And physically, this can be interpreted as this number, as I said, should be interpreted as the total number of the 7 branes that hit the heterotic string. So these are the perturbative 7 branes interacting with the heterotic string. And this is counting this number of the 7 branes. And therefore, it has to be integer even for physicists, but this can be proven also mathematically. And therefore, it follows obviously from this fact that HI has to be bigger or equal 1/12 as long as it's non-zero. And this is important because it gives a finite positive bound. As long as HI is non-zero, it is bounded from below by this something finite. And this will play a very important role later. Now, we may assume, without loss of generality, that the blow-ups with bigger horizontal multiplicities are performed earlier. In other words, this sequence of the horizontal multiplicities HI is forming a non-increasing sequence. And we denote by R prime where they first drop to 0, if at all. Okay, so R prime could be R if they do not drop to 0. Okay, then we are finally ready to address the bounds on R prime and R in turn. So let's start with R prime. So we start by claiming that this total horizontal multiplicity, which is the sum of all HIs, is bounded from above by a certain number. And without getting you all the details of this statement, let me just assure you that this upper bound follows from the global constraints, these two global constraints, one at the initial surface Z0, the Hertzsprung surface, and the other at the final surface of the blow-up sequence ZR. Then this sum of HIs, H total, is a sort of an interpolator between these two global constraints. So these two global constraints are essentially from the compactness of the surface Z, which is our internal space, so this is to do with the gravity in your EFT. And this sum plays a role of an interpolator between these two global constraints. That's what's happening. And therefore, obviously, we can see that R prime is bounded. So why is it? That's because, as we saw last slide, as long as HI is non-zero, which is by definition the case up until R prime minus 1, because that's the sort of all the positive HIs we're collecting together, we know that they should be bigger or equal 1 over 12. So we must get something, some upper bound, definite upper bound from here. And indeed, as for an explicit upper bound, what we have for R prime is this. So R prime is less equal to the total sum 28 of the horizontal multiplicity times the lower bound for each of those horizontal multiplicity. So it gives times 12. So we have 336 as a definite upper bound on R prime. Okay? And next, to bound R, we will make use of two claims. So claim number one is this. So if HI is 0, then the blow-up point ZI should lie in two vertical curves C1, 2, as in this picture. So then the blow-up at this ith level would be something we can call a double blow-up, because we are blowing up at a point of the two vertical curve intersections. So why is this the case? That's because otherwise, i.e., if the blow-up point lied instead in a single component C instead, then upon blowing up through a, so to speak, a single blow-up, then the coefficient of the exceptional divisor of this blow-up in this induced divisor at the I plus 1th level would become negative, and this is due to the 1 over 6 Elsiness imposed on the previous pair level. And now the claim number 2 is this. For any point small z inside ZR prime at the end of this positive multiplicity blow-ups, for any point there, the number of blow-ups over z that will have been performed through the sequence after R prime will be bounded from above by 11. And this can be seen easily from the maximal case where the two vertical components C1, 2 of BR prime both saturate the 1 over 6 LC bound. And if you're familiar with this conformal metal list, this situation corresponds precisely to the EA times EA conformal metal. Then again, we see that R minus R prime is going to be bounded from above, because there are only R prime points of vertical curve intersections inside the ZR prime, which can be further blown up, each 11 times at most, right? So what about the explicit bound on R then? Obviously, due to this fact, R minus R prime is bounded from above by 11 times R prime. But from the previous slide, we know that R prime itself is bounded from above by some 300. So we get the bound on R minus R prime is 11 R prime. So R is bounded from above by 12 R prime, which is then bounded by 4032. So this is some concrete explicit bound we can impose on R, and therefore on the tensor multiply count up to some shift. Now that we have some bound, in order to assess whether it's a good bound or not, let me show you a quick record space quickly here, which has R equals 192. So this might be familiar to some of you already. So this example is obtained by blowing up the Hertzsprung surface F12 192 times in this particular way. And as you can see, there are lots of 12-12, which means E8 times E8 conformal metal. So each of these blocks, 12-12 blocks, is an E8 times E8 conformal metal carrying 11 tensor multiplets. And now we know that this record space with R equals 192 is in fact a maximal surface because this work shows that number of tensor multiplets should be less than or equal to 193 for sure. So they argue for this sharp bound essentially via the anomaly constraints under certain assumptions. So the assumptions they make are largely twofold. One is the completeness of the classification results in these papers of the superconformal and little string theories. And the other assumption they make is the emergence of tensionless BPS string in the boundary of the tensor moduli space. But the point I'd like to make here is that, okay, if you're a physicist, then we would believe in anomaly cancellation for sure for the gauge anomalies, and also gravitational. And if you also buy the assumptions they make, up to you, then we should believe that this bound should be definitely bound, at least to physicists. Whereas the bound we have computed from a slide ago is some 4,000. So of course we should ask, can we do better? It turns out we can. And in order to show you how this improved bound arises, let me first prepare for some basic stuff here. So we consider special fibers of this P1 vibration at the end of the blow-up sequence ZR. Okay, so every Zi had a P1 vibration, and at the end surface ZR, we consider the special fibers of this vibration. We of course say that a fiber is special if it has undergone some blow-ups itself, i.e. if it is a reducible fiber containing some exceptional divisors in it as components. Then we define the multiplicity of each special fiber in this appropriate manner in terms of the discriminant divisor, but now at the level of the P1 base of the surface Z. Then next, what we do is to group the special fibers based on their multiplicities, whether they are bigger or smaller than some certain reference number, which we take here to be 3/4. We just classify them into two groups. So X low and X high. They are the points in the P1 base where these special fibers lie. And if this label mu SF, if of the special fiber is less than 3/4, we put it into X low. If bigger or equal, then we put it into X high. Okay? In fact, in the paper, we make use of a threefold grouping, but in this talk at least, I just wanted to give you the flavor of what's going on in this bounding strategy. So what is the benefit of such a special fiber grouping? We first observe that the special fibers over X low, i.e. those with low multiplicities, cannot have too many components. This is because the individual components cannot have too big a multiplicity in the full fiber, thereby limiting the number of double blow-ups which have been performed for that fiber. Then the intuition from here is that perhaps a big portion of the entire number of the vertical curves at the endpoint of the blow-up sequence should come from the X high special fibers with some large multiplicities. But then we have this claim that the number of such fibers with high multiplicities cannot be bigger than 2. And this follows from the compactness of the base. And here by the base, what I mean is the base of the P1 base of the surface ZR. Then the next observation is that the special fibers over X high with high multiplicities cannot have too many components either. It's not just the low multiplicity fibers, but also the high multiplicity fibers which cannot have too many components. So you see the flavor of how the number of components are being bounded here. And this last observation follows from the compactness, but now along the fiber. So it's interesting to observe that all of these constraints are coming from the compactness of the surface Z, both along the base and the fiber thereof. Then, with a bit of tricks, which I probably won't discuss here, which are nevertheless written carefully in this paper, we can improve the upper bound, which used to be 4,000, down to 566. And just to say in words what's happening here, what we're doing is to bound the number of vertical curves at the end of this blow-up sequence in a sort of fiber-wise fashion, treating the fibers with different multiplicities differently, grouping them first into, say, these three different groups. Furthermore, we distinguish double versus single type blow-ups, keeping also track of the horizontal multiplicities along the way. And going through some song and dance, in the end, we can find some explicit upper bound, which is much better than the previous rough bound, which was 4,000. You might say that, okay, this is not as good as 192 still, but I must emphasize that the way we improve the bound here still leaves much room for even further improvement. After all the ideas are out there already. The boundedness has already been made manifest, and the strategy we propose here has been proven to be practical enough to give rise to some explicit bounds. Perhaps what we haven't used here is the computer science. So in the spirit of this conference, we have used math and physics, and perhaps with a bit of input from computer science as well, we could optimize the bound even better, pushing it down to 192, we believe. Okay, with that, I'd like to conclude. So what have we done? We have launched a program of systematically, explicitly, and uniformly bounding the spectra of supergravity EFTs with minimal supersymmetry. In order to gain intuitions at this initial stage, we have specialized to 6-dimensional F3 vacua, focusing on the tensor sector, and we have proposed a systematic bounding strategy. We have seen that two geometric structures play a key role in our bounding strategy. One was the vibration of the integral space Z, not the elliptic vibration, but the P1 vibration you can find within Z. And the other was the particular singularity structures of the pair Z, B, where B encodes the 7 branes roughly. And interestingly, these two geometric structures are physically interpreted very naturally as the heterotic string and the decompactification threshold, thereby exhibiting an intimate connection to the conjectured universal asymptotic physics as claimed by the emergent string conjecture. And eventually, by exploiting these two structures, along with some other global constraints coming from the presence of gravity in the effective field theory, we have been able to obtain an explicit bound on H11 and therefore on the tensor spectrum T as well. Now, before closing, in the remaining couple of minutes maybe, yes, I'd like to remark on these 3 specializations made up here in 3 colors. So remark number 1 is that while we have focused on the tensor sector mostly, an explicit bound on it leads to the associated finite bounds in the other sectors too. Number 2, while we have analyzed the F3 vacua, given the clear physical interpretation of the key structures as well as some other structures we've making use of, the strategy would naturally generalize to the supergravity setting without relying a priori on the string theoretic origin of the EFTs, of course modulo certain physical conjectures. Number 3, our bounding strategy does not rely on the 6-dimensional anomaly constraints, and in particular, not on the specific form of the anomalies in 6 dimensions. And this seems to hint that it should be generalizable to the 4D n equals 1 setup as well, which we have started discussing with Kocher, and also my postdoc, Jeren Kotlevsky at IBS now, as well as his student, of which name I forgot. We have to meet here, in fact. But in fact, even before getting down to 4D, already in 6D, the anomaly constraints have not been established geometrically. So already in 6D, it's very, very interesting to realize that such a bound could just be derivable without relying on the anomaly, at least explicitly. So the final remark concerns a bit of mathy situation here. So the addressing boundedness has been a major goal to achieve in algebraic geometry in general. And in the context of my talk today, what's known in the math literature include the boundedness of the Calabi-Yau varieties in dimension d bigger or equal to 3. And they are all very recent. It's like 2004, sorry, not yet, 2024, 2025. But all of these are at the level of the abstract boundedness. On the other hand, our program has towards the explicit boundedness, the effective boundedness, which in many cases is much more useful for physics, in my opinion. And I must say that many of these techniques that have been well developed in birational geometry, which somehow have not been well enough adopted in the string theory literature somehow, can be very useful to this end, like it was the case in my talk. So it will be exciting to see how this interplay could tell us more about any exciting new results in sort of understanding the rigid structure of the full set of consistent effective field theories, and I'd like to stop here. Thank you very much.